Good morning and welcome to this next lecture on vibrations of plates and shells. We are now looking at mode shapes and resonances. And in the last class we looked at a beam. We looked at two cases. One was a cantilever beam and the other was a simply supported beam. So in the beginning right now I just want to show you some animations of mode shapes. As I said last time, vibrations is an elective in most universities, so some of these are not known to students. So let me show you how a cantilever beam mode shape looks like. So this is the first mode of a cantilever beam. Okay. So on the left the displacement is 0 and the slope is 0. Okay. So W at x equal to 0 is 0 and del W del x at x equal to 0 is 0. On the other side you have second derivative of W and third derivative of W 0. Okay. That means the moment is 0 and shear force is 0, and therefore the displacement and slope are unknown or unspecified, are free. Okay. So this is the first mode of a cantilever beam. Okay. You will notice that there is only one point where it is 0, everywhere else the displacement is non-zero. Okay. Now I will stop this and change it to 2 here. So we should see the second mode shape now. Okay. So this is the second mode shape. Again you can see that the same boundary conditions hold. Okay. At the left hand end displacement and slope are 0. I have not taken enough points, so the discretization is a little bit rough, but that is okay. You can see that the slope goes to 0 gradually. And again on the right hand side shear force and moment are 0 and therefore displacement and slope are free. Okay. Another thing is, in the second mode there is a node point. Okay. There is a fixed point where the displacement is 0 for all times. Okay. So this is the nature of mode shapes. You will get such node points. Okay. So such zero displacement points are called nodes, whereas the maximum displacement points will be called antinodes. Okay. So I will stop this and show you the next mode. The next is third mode. So now you can see there are two nodes within the beam and the edges again satisfy the same boundary conditions. Let me go one last time to a higher mode. This is now the fourth mode. Okay. So as I said, it is not very finely discretized. It looks like bunch of joints there. If I discretize it more, I will get a finer line. So again extra nodes 1, 2, 3. So you have 3 nodes now and 3 antinodes, and this mode satisfies the same set of boundary conditions. So that is very important. All the mode shapes satisfy the given boundary conditions. Okay. both force type and displacement type. Okay. So, I will stop this again. So, that was a cantilever beam, that means clamped and free. Okay. Now, I will show you mode shapes of a simply supported beam. So, let us see. So, this is a simply supported beam. Okay. On the left and right displacements are 0, also on the left and right moments are 0, and that is second derivatives of W are 0. Okay. So, this is the first mode, and there is no node point within the beam, no 0 displacement point within the beam. Let me close this and I will set n to 2. So, now you will see a single node point right at the center. Okay. So, you can see this is a pure sinusoid. So, simply supported beam modes are sinusoids, clean sinusoids. Okay. So, now along with the number n is 2, you see 2 half cycles. Okay. So, you have see one half cycle, a node, and then the other half cycle. For n equal to 3, okay. So, now you see 2 node points within the beam length and 3 antinodal points. Okay. And it is in the nature of modes that as n goes higher, it becomes more and more wavy. That means the strain energy goes up. Okay. And we will see a little bit later that it also means that the the kinetic energy has to match the strain energy. Okay. So, the kinetic energy being proportional to frequency squared, as the mode number goes up, the natural frequency value goes up. I will close this and show you the fourth mode. So, this is the fourth mode. Okay. So, again my discretization is not that good. Let me just try to discretize once. Okay. Yeah, instead of 20 I took 100 points. So, now you see it looks much better. So, this is the fourth mode, and for the simple support case you have 4 half cycles. The 4 refers to the number of half cycles. So, the 0 displacement points, they hold the 0 displacement forever. Okay. It does not change, and also the maximum point, the antinodal point does not change. So, that is as far as beams is concerned. Now, we will get back to some derivation and start looking at plates. Okay. So, now let us look at plates, okay, or let us look at rectangular plates first. Rectangular plates. So, let us look at a diagram. So let us say this is my middle line, this is x direction and that is the y direction. Okay. Now there are many ways to derive mode shapes, but as I said, being a fundamental course, I am sticking to the textbook and I will do it the way the textbook does it. So let us say both these sides, okay, this side, okay, this side and this side, the two x edges are simply supported, okay. So we will begin with that. So this is x equal to 0 and this is x equal to a, both these edges are simply supported, okay. So what does it mean in terms of the displacement u3, which is a function of x comma y comma t. So x equal to 0 for all y and t, displacement is 0. So this displacement is 0. Then u3 at x equal to a for all y comma t is equal to 0. So the displacement here is 0. Then mxx at x equal to 0 comma y comma t equal to 0, okay. So the moment here is 0 and similarly the moment here is 0. So mxx at x equal to a comma y comma t is 0 to begin with, okay. And what is our plate equation? Plate equation is this: d del 4 u3 del x4 plus twice del 4 u3 by del x square del y square plus del 4 u3 by del y4 plus rho h mass per unit area del 2 u3 del t square is equal to 0, okay. And we always say that for a mode shape we are looking at a harmonic solution. u3 x comma y comma t is equal to sum u3 function of this space and vibrating at a single frequency. So if we substitute this into this, okay, we remove the frequency or we remove the time, so we get del 4 u3 del x4 plus twice del 4 u3 del x square del y square plus del 4 u3 del y4 minus rho h omega square u3 equal to 0. And the boundary conditions earlier on this translate to the boundary conditions on this, okay. So u3 x equal to 0 comma y is 0, u3 x equal to a comma y equal to 0, del 2 u3 del x square x equal to 0 comma y equal to 0, del 2 u3 del x square x equal to a comma y equal to 0. Okay. Now, because along the x we assumed, or x edges we assumed simple supports, so we are going to say that our solution is separable, and we can write it as sin m pi x over a. Sin m pi x over a satisfies this simple support conditions at x equal to 0 and x equal to a. Okay. So, if we now substitute this, okay, let us say this is 1 and we substitute it into this equation here. Okay. So, what we get is d4 y dy4 minus twice m pi by a whole squared d2y by dy squared plus m pi by a whole fourth minus rho h by d omega square y is equal to 0. Now, this is a fourth order ODE, okay, and so we can substitute this form here, sigma I equal to 1 to 4 C I e to the power of lambda I y by b. Okay. If we do that, we get an equation in lambda I, which is lambda I by b whole to the power 4 minus twice m pi by a whole squared lambda I by b whole squared plus m pi by a whole fourth minus rho h by d omega square equal to 0. So, we get a polynomial. Actually, if you substitute not with the summation, okay, just y of y as some constant into this, in here you will get this equation, and it is a polynomial of fourth order. So, there are 4 roots for lambda I. So, what are those? Lambda I is equal to plus minus b by a m pi square root of 1 plus or minus k. So, this gives you 2, that gives you 2. So, you get 4 roots. Now, what is the value of k? K is given by omega by m pi by a whole squared square root of d by rho h. Now, this omega will be the natural frequencies, actually omega m n, and this expression happens to be the resonance frequency of a beam, okay, a simply supported beam, except that d has 1 over mu square in it, okay, in the denominator. So, slightly higher values than normal beam simply supported modes. However, as the beam behavior happens in one direction of the plate, the y direction also gets strained in case of the plate, okay, which is not there in case of the beam. Beam, there is only x behavior. For a simply supported beam, there is only x behavior. And so these are the natural frequencies, slightly higher because of 1 minus mu square. However, along with this behavior, in the y direction of the plate, there is strain happening due to modes in the y direction. Okay? So there is more strain energy. So what will happen is that these omega mn, every value of n will be greater than this, so that my k will be greater than 1. Okay. So now, with the knowledge that k is greater than 1, what we get is lambda 1 is plus rho 1, lambda 2 is minus rho 1, lambda 3 is j times a rho 2, and lambda 4 is a minus j times a rho 2. If we use these 4 values in here, okay, in the y, and simplify, what we will get is rho 1 is equal to b by a m pi square root of k plus 1, and rho 2 is equal to b by a into m pi square root of k minus 1. And substituting these values, there can be a further simplification. If we simplify it, which is there in the book, we can write y of y as a cos hyperbolic rho 1 y by b plus b sine hyperbolic rho 1 y by b plus c cosine rho 2 y by b plus d sine rho 2 y by b. Okay. Now, let us first do if the other two edges are simply supported. So we have a simple support at x equal to 0, we have a simple support at x equal to 0, but what if it was simply supported on the y edges also? Okay, x and y. That means now the small u3 for all x at y equal to 0 for all time is 0. Okay, then u3 for all x at y equal to b for all time is equal to 0. Then myy, okay, which is this sort of moment, okay, myy for all x y equal to 0 for all time is 0, and myy for all x at y equal to b for all time is 0. These are the boundary conditions now. Okay, and this translates to this y, where I get y at 0 is 0, y at b equal to 0, d2y by dy square at 0 equal to 0, and d2y dy square at b equal to 0. Okay. Now, if these are applied to this, you get 4 equations, and that can be put in a matrix form. We just do it for now. 1 0 1 0 cos hyperbolic rho 1 sine hyperbolic rho 1 cos rho 2 sine rho 2, then rho 1 squared 0 minus rho 2 squared 0 rho 1 squared cos hyperbolic rho 1 squared sine hyperbolic rho 1 minus rho 2 squared cos rho 2 minus rho 2 squared sine rho 2. Then you have A, B, C, D, and these have to be 0. Okay. And so for non-trivial values of A, B, C, D, if the 0 has to hold, then the determinant of this matrix must be 0. Okay. And the determinant ends up looking like this: rho 1 square plus rho 2 square whole squared sine hyperbolic rho 1 sine rho 2 is equal to 0. Okay. So now in here, as k is bigger than 1, rho 1, rho 2 are real. Okay. So what happens now is that this can't be 0, and for no value can sine hyperbolic rho 1 be 0, and therefore the only option is sine rho 2 has to be 0. Sine rho 2 has to be 0. Rho 2 has to be 0, which means rho 2 has the form n pi, because sine goes to 0 for many values, n equal to 1, 2, okay. Now as a result, what happens? As a result, what happens is rho 2 being equal to b over a m pi square root of k minus 1, what happens is the k n becomes equal to n by m whole squared a by b whole squared plus 1. Okay. And then this kn is equal to omega mn by m pi by a whole squared into square root of d by rho h, and therefore omega mn becomes n square a square by m square b square plus 1 into m pi by a whole squared square root of d by rho h. Okay. So which becomes equal to n square a square by m square b square m square pi square by a square plus m square pi square by a square square root of d by rho h. This goes with that, this goes with that, and finally I get the well known formula square root of d by rho h m pi by a whole squared plus n pi by b whole squared. Okay. So, this matrix has kn values in it. Okay. So, these are the kn values. Okay. So, if you substitute the relevant kn values, okay, if you substitute the relevant kn values, then what happens is that this matrix becomes singular. That matrix becomes singular, and therefore what happens is you cannot independently solve for ABCD. One equation becomes dependent, so that you can solve for 3 of these constants B, C, D in terms of A, or A, D, C in terms of B, like that. You can solve only one for the in terms of the other. So, in one form what happens is that the 3 equations or the 4 equations can be rearranged as cos hyperbolic rho 1, sin hyperbolic rho 1, cos rho 2, rho 1 square, 0 minus rho 2 square. Okay. As I said, 3 of the constants can be solved for in terms of the 4th, because the matrix has lost its rank. So, this is how the rearrangement of equations looks like. Okay. A, B, C are going to be solved in terms of D. Okay. Now, if you look at this, it turns out the first equation is A plus C equal to 0, which implies A equal to minus C. Then last one says that rho 1 square A minus rho 2 square C equal to 0, which if I substitute A as minus C, I get rho 1 square A plus rho 2 square A equal to 0. Okay. Neither rho 1 square is 0 nor rho 2 square is 0, which implies A is 0, which implies C is also 0, and which implies in the second equation that B cos rho 2 is equal to minus D sin rho 2. Okay. So, this can also never happen. Okay. B times cos rho 2 cannot be equal to D times sin rho 2. As a result, what happens is that B, because sin rho 2 is 0, okay, sin rho 2 is 0. So, B cos rho 2 is 0, and since cos rho 2 is not 0 where sin rho 2 is 0, B must be equal to 0. So, A, B, C are 0. Okay. So, in the expression for the displacement, which if you recall had y of y and so many things, finally D sin rho 2 y by B. Okay. So, then rho 2 is n pi. So, this ends up as D sin n pi y by B, okay, in the y direction, and therefore the total displacement across the plate for 3 in the m comma nth mode x y is d sine n pi y by b into sine m pi x by a. We started off by saying that it is simply supported in the x direction. So, that mode shape comes in, and this we started off as y of y, okay, and we have found that y of y is another sign in the y direction. So, this happens to be the mode shape. I will stop here for this lecture. We will continue in the next class. Thank you.